All right, day 2 of exponentials. So tonight's focus is on writing exponential growth and decay functions. All right, so we're going to start with this little do now problem. I want you to do this before we jump into today, based off what we talked about yesterday. So given the exponential functions, I want you to identify the initial amount, the rate of change, and whether it's growth or decay. And is it in the Algebra 1 form or the Algebra 2 form? So take a moment, pause it, and I'll get my answers worked out, but pause it and try it on your own. All right, so here's what I've come up with. I said this is the Algebra 1 form. Probably won't get to see that on our exam, but it's going to be pretty basic. My initial amount is 125. This number is bigger than 1, therefore it's growth. And I know that because this x is by itself. 1 plus the rate equals this number. My rate is 0.035, therefore 3.5%. Yes, I know I went through it fast, but this should just be a quick review from yesterday. B, welcome to Algebra 2. Let's get the initial value out of the way. I said my initial was 5,000. Hopefully you agree. I cannot answer whether this is growth or decay until that x is by itself. So it's simple. We said yesterday, just move that 2 inside. So I got 0.64 inside. That's less than 1 decay. 1 minus r equals 0.64. So I said 36% was my rate of change. All right, so this is huge on our exam. We've said exponentials, growth and decay. So I want to be clear one last time here. This represents our final amount. Let's get this in our notebook. A is our initial amount. R is our growth rate or decay rate. And T, of course, represents our time. The difference between growth and decay is that the R value is either... the R value and the A value are always positive, but what this turns out to be is either greater than 1 or less than 1. So here we are ready for our first attempt on this problem. So let's go ahead and label this question A and this question B. The inaugural attendance of an annual music festival is 150,000. The attendance increases by 8% each year. So what jumped out at you? Well, bam, initial. So circle that, put an I. Increases. You've got to jump out growth right there if something increases. So part A says write an exponential function that models the attendance after t years. So you better have a t in it. So all I'm saying is y equals my final amount equals my initial amount. We said it's growth, so 1 plus the rate. Now 8% isn't the rate. What is my actual rate? 0.08 raised to the t. Okay, and I want you to clean that up. Let's not be sloppy. So that's 150,000 times 1.08 raised, to the t. And that would answer part A, right? An exponential function that represents the attendance after t years. Part B says, how many people will attend the festival in the 5th year? So notice they gave me a year. That represents time. So again, very basic. All they want you to do is plug the number 5 into the time, and they want to know what is that final amount. So y equals 150,000 times 1.08 raised to the 5th, nothing fancy. Now, the only fancy thing they got on us is our rounding. Round to the nearest 1,000. Okay, so again, I'm just throwing that in my calculator all on one line, little plug and chug. And I've got 220,399.2115. Hopefully you can verify that on your end. Now, it didn't say thousandth. They're not talking decimals. They said 1,000. So let me find the 1,000 place. There's my ones, my tens, my hundreds, thousands. Let's box or kind of underline that piece. I'm rounding at that number. So I look to the number before it. If it's less than 5, I leave it alone. So I'm going to say this is 220,000 people. All right, number 2. The value of a car is $21,500. Its value depreciates 12% each year. So let's stop and identify what we have. 21,500, that represents your initial. If something depreciates, did it get bigger or smaller? Did it grow or decay? I would definitely say this represents decay. And 12%, think about what we'd use for an R value then. Hopefully you're saying 0.12. All right, so again, let's go A and B. A, write a function that represents the value in dollars of the car after t years. So this time I'm going with decay. So my initial value is 21,500. 1 minus the rate to the time. So I'm going to say that's 21,500. 1 minus 0.12 to the time. And again, I'm just going to clean that up. 21,500, 0.88 to the t. Part B, use this function to find how long it will take to the nearest tenth of a year for the car to be valued at 15,000. So now what did they give me and what do they want? They want a year. So the question is, what is the time when the final amount is 15,000? Okay, so I'm looking for t, but they gave me y basically. So here's where it gets fancy, and you have to have a calculator to solve this equation. It's impossible without. So I've got my 21,500. That's my 0.88 to the t. Okay, so now here's what I always say to myself. Who is the t sitting on? The 0.88. I kind of box it in for myself. I got to move everybody to the other side. So I'm first going to divide both sides by that 21,500. Okay, now, numbers aren't always going to be nice. That's why we have a store button on our calculator. If you can go math frac, that's always easy too. So here I got 0.88 to the t. When I type this in, I'm actually going to hit math frac, and I think it reduces to 30 over 43. Now I want to remind you, this is exponential because the exponent is where the variable is. So maybe make a note, exponential. The only way to solve an exponential is to use logarithms, and that is to take the log of both sides. So you can use the ln, the natural log, or the common log, log. It truly doesn't matter. You just have to be consistent. So I'm going to take the ln of 30 over 43, and I'm going to take the ln of this side. Now you have to use your log properties. When you take the ln of an exponential, the exponent comes down in, I think I heard you, front. So it's going to be t ln of 0.88. Okay, again, what are the log rules? When you take a log, the exponent comes down in front. Now my goal is to get this t alone, so I'm just going to divide both sides by the ln of 0.88. And again, not numbers you know without a calculator. And I get t equals 2.8. And remember, this is years. Number 3, an apartment purchased 4 years ago for $80,000 was just sold for $105,000. Assuming exponential growth, approximate an annual growth rate to the nearest percent. Whew. Okay, so annual meaning that t value has to be a 1 up in the exponent. Not really t equals 1, but the t value must be a 1. So let's talk about what we know. If I went from 80,000 to 105,000, what has to jump out at you? They said it's exponential, but clearly it's exponential growth. This thing jumped in price. Okay, so I'm going to start with my formula. Y equals a, 1 plus the rate to the t. Y represents my final amount. This finally sold for $105,000. The initial amount was $80,000. And let's see, I don't know the rate, so I'm going to leave it as 1 plus r, but I do know that the time was 4. All right, so now I got to solve for that rate. So notice this is all attached to that fourth, so I'm going to divide out the 80,000. And again, I'm going to get some crazy decimal on my calculator, plug and chug, make sure you're going along with me. And I get 1 plus r to the fourth. I'm actually going to store that into alpha a, so to be consistent. Now, how do you solve this problem? Well, how do you get rid of a power of 4? Well, if it was squared, how would you get rid of a square? You take the square root. So how do you get rid of a power of 4? We're going to take the fourth root of both sides. Okay, and the fourth root power are going to undo each other. So here I'm going to get 1 plus r, and here I'm going to get 1.07034. And I'm going to subtract my 1, and I'm going to get 0.07034. So I can say my rate is actually 7%.
All right, the next few problems get a little more difficult. What if the word problem does not give you the rate of change as a percent? So you're going to look for keywords. So let's jot this down. If it's exponential growth, we're going to look for words such as doubling, tripling, quadrupling. If it's exponential decay, we'll look for words such as half or half-life or a third, etc., something that's getting smaller. So our first example, an initial population of 20 mice triples every year. So what jumps out at me? Well, clearly the triples every year should jump out. So let's go ahead and highlight that. If it's tripling, we know this is exponential growth. Something is getting larger. So I'm saying 1 plus the rate has to equal 3. So write an equation that models the population after t years. Well, look how simple this is. It's my initial amount, so my final amount equals my initial amount. And literally, when I see tripling, I'm literally going to put in the number 3 raised to the t. It is tripling every 3 years. So again, initial, and this takes care of that word triple. All right, let's try another one. The half-life of a medication is the time it takes for the medication to reduce to half its original amount in a patient's bloodstream. Sounds kind of obvious. A certain antibiotic has a half-life of 1 hour. A patient takes 500 milligrams of the medication. So let's highlight some things that stick out. The first thing you should have jumped at was half-life. Okay, so if something's taking half the amount of time, we know that that's exponential decay. Okay, it's not getting larger, it's taking half the amount of time. That's decay. So I know my 1 minus the rate has to equal 1 half. So if I subtract that 1 over, clearly my rate is also going to be 1 half. Write a function a of t, so don't call it y equals this time. They're specifically saying call it a of t. So my final amount equals my initial amount, which is 500. The rate we just said is 1 half raised to the t. And that's simple. All right, so now we kind of step up into the Algebra 2 type question. What if the word problem mentions the growth or decay rate over a specific period of time? So let's kind of highlight that for ourselves, a specific period of time. So A, the half-life of a medication is the time it takes for the medication to reduce to half its original amount. So it's very nice to keep reminding you of that. A certain antibiotic has a half-life of 1 hour. Okay, so highlight that in your notebook. The half-life is 1 hour. And the patient takes 500 milligrams, so there's your initial amount. What they're telling you to do, since the half-life takes 1 hour, they're saying take your t and divide it by 1. So again, let's get that in our notebook written out. Take your t and divide it by 1. So this is what the function would look like. Now compare that to question B. The half-life of medication is the time it takes to reduce to half its original amount. A certain antibiotic has a half-life of about 3 hours. Highlight that for yourself. A patient takes 500 milligrams. So notice how they start the equation this time. My final amount, A of t, equals my initial. My rate is half because it's half-life. But it happens every 3 hours. So now I'm taking that t and I'm dividing by 3. Okay, so again, let's get that written out nicely in our notebook. The difference, this is every 1 hour, so I'm dividing by 1 technically. And this is every 3 hours, so I'm dividing by 3. Question 6. Suppose that a water tank is infested with a colony of 1,000 bacteria. So let's stop there. What are they telling you right off the bat? The initial amount. If in this tank the colony doubles, ding, 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 there's the next keyword. Let's highlight that. If something doubles, it's getting larger. So that's exponential growth. And it doubles every 4 days. So I'm saying I've got to catch that and say, okay, take your time and divide it by 4. So now let's go ahead and write a formula for A of t. So A of t equals the number of bacteria after t days. So I'm going to start with 1,000 bacteria. It's doubling, so that makes my rate obvious. That makes it a 2. And it's not happening every day, so not just to the t, it's happening every 4. So I'm going to divide that by 4. Number 7, lead-209, a radioactive isotope, decays to a non-radioactive lead over time. The half-life of the lead-209 is 8 days. So holy smokes, it sounds like that's a lot of information. You just got to slow down and pick out the keywords. So what jumped out at me? Well, not only did I see the word half-life, it clearly said the word decay there. So I know right off the bat I have exponential decay. By how much? Half, because it's half-life, half the life is remaining. Now here's the catch. It doesn't happen every day, it happens every 8 days. So I know I'm going to take my time and divide it by 8. Write an equation to represent the amount of lead after T days. All right, pause it, write your equation, let's see if we get the same thing. All right, now, I don't know if I read that sentence out loud. It does say, suppose that there's 20 milligrams, so I know my initial amount's 20. Again, we talked about our half-life happening every 8 days. Last one, titanium-44 is a radioactive isotope such that every 63 years, its mass decreases by half. For a sample of titanium-44 with an initial mass of 100 grams, write a function that would give the mass of the sample remaining after any amount of time. All right, so again, I just want you to pause it, pull out the 3 key ideas, just jot them down, and then write the equation. So here are the things I pulled out. I highlighted them every 63 years, so I said I'm going to have to take my time and divide it by 63. Decreases, so I said, okay, bam, that's decay. By how much? Half, so there's my rate. And the initial amount is 100. So I'm just going to say y equals my initial 100 times my half-life raised to the t over 63. And there you have it. Well, just like normal, we're going to get some great practice tomorrow. Hopefully this wasn't totally brand new to you and it did feel like a little bit of review. And we'll have a great night.